Section 10.5 Vectors in a Plane. Our objectives are to find the components and magnitude of a vector and to perform scalar multiplication of vectors, vector addition, and vector subtraction. A vector is a quantity with both a direction and a magnitude. I.e., if we talk about a westerly wind blowing at 15 miles per hour, so the 15 miles per hour would give us our magnitude, and the westerly wind would be our direction. So they are directed line segments, usually denoted by U, V, and W for our variables, also have an initial and a terminal point. Now, these are often confused with array, which has a specific direction and an infinite length. Just because we have the arrow on the end of this doesn't mean it's going on forever, because a vector has a specific length and a specific direction. So you kind of keep that in mind as you're doing these problems. The standard position of a vector is when the initial point is at the origin, and the magnitude of a vector is the length of a vector. And again, remember that it has a specific direction and a specific length. Now, for this, usually there's a point on the end right here, and then of course this arrow would denote our terminal side. So this point here would be the initial point, or our starting point, and this would be the terminal point where the arrow is. And for these, we can denote the length of this by using these double lines, and if you use uppercase letters like this, we have, and you can put an arrow above, that denotes the magnitude of the line when you use those two lengths like that. And notice that when the ends are not specified, we use bold case lower letters. But the problem with bold case lower letters, unless you're using a computer or something, it's hard to make your letters look like they're boldface. So a lot of the time you'll see a line like this on top of the variable when somebody is writing it out. So that also means that you have a vector. And the length of this vector u would be written like this. So we can write it like that when we're not giving the terminal and initial points that we have. So these are just examples of vectors and what they look like. Okay. When vectors have the same direction and magnitude, they are said to be equal. Note, they don't have to have the same initial and terminal points. So these give us equivalent vectors, and it allows us to basically move vectors around on our coordinate plane and positioning them in different positions. So again, if you look at vector u here and vector v for the first pair, these are equal vectors because they are the same length and same direction. Now if you look at the next pair, vector u and vector v, for both of these, because vector v is going in this direction, these are not equal. If you look at vector u and vector v for the next pair, they are going the same direction. However, they are not the same length. So therefore, these are not equal. And these were the same length, but not the same direction. And for the last pair, vector u and vector v are not the same direction, nor the same length. So therefore, vector u is not equal to vector v. So that's just talking about equivalent vectors. If we want to find the length of a vector, let's say we're given a different couple of options. So if we were given a vector where the initial point would be the origin and the ending point was this point right here, which is we're going to call AB, and I want to find the length of the vector. Well, if you recall from geometry and algebra, if I want to find the length of this vector right here, and I know that that point is A and B, well then I know this length is A, and this length is B here, so then, and this makes a right angle, so then I can use the Pythagorean theorem in order to figure out what the length of vector V is going to be. And so we would have, remember that A squared plus B squared equals the length of the vector squared. So in this case, if we do the vector V would be equal to the square root of A squared plus B squared, and that is actually written right here. So that gives us our length of vector v using that formula right there. So again, that's just the Pythagorean theorem, so it's nothing really new. If I wanted to find that angle of theta, so the direction, think about your right triangle trigonometry. So this is really going to be more in the next section, but if I know this is theta and I have, let's say, length A and length B, and I know what the length of the vector is, I can figure out what the angle of theta is by doing right triangle trig. So if I wanted to do opposite over hypotenuse, I know that I have sine. So let's say I did the sine of theta. The sine of theta would be equal to b over the length of the vector. And then I could solve for b by saying the vector times sine of theta. I can also do the same thing for the cosine, but I'm not going to write that down right now because we're going to do that later, but just so you can see. Now, the next one is, notice that the initial point is not on the origin. So if the initial point is not in the origin and the terminal point, then you have to do something a little bit different. So let's say that this initial point right here is x1, y1, and then this one right here, we have x2, y2. Well, then to find the distance from here to here, you're just going to subtract y2 minus y1, and from here to here, you're going to subtract x2 minus x1. And when you do that, that allows you to find the length of your vector using the same thing that we used over in the first one, which was the Pythagorean theorem. So the square root of x2 minus x1 squared plus y2 minus y1 squared gives us the length of our vector PQ for that. Now, there is another way that we can write vectors using our horizontal components and vertical components. So the component form for a vector, for the first one that we have right here, we would actually write it with these little like arrows. So A comma B would denote the fact that we have the vector AB. And we could do, of course, the same thing with the other vector that we have as well. So again, these little greater than and less than signs just means the component form of the vector. And again, they have two components, the horizontal and the vertical. And if you want to find the component form of the vector, if you're not if you don't have a standard vector position at the origin, then you can just subtract the two like we did for the Pythagorean theorem. So if you subtract the point x2 minus x1 minus y2 minus y1, and then you would get your vector. Now for this, it's always the terminal point subtracted by the initial point. And for this subtraction, the order matters. So you always have to do the, again, terminal point minus the initial point. And notice that it's your x's, comma, your y's, just like you would write a coordinate point. So instead of writing a vector as an angle and a magnitude, we write it now as its x and y components. So again, the x, y components are just the horizontal and the vertical. So it's just a different way of writing the point. Okay, so let's go ahead and look at this first example. We want to show that PQ is equal to OR. If we want to show that these two vectors are equal, then that means we want to figure out the to see if the length of the vectors are going to be equal. So let's go ahead and do PQ first. So if I'm figuring out the length of PQ, I can do that by using the fact that we're trying to find this distance, the horizontal, and this distance right here. So I know that with the formula we used before, we can just subtract the x coordinates and square it, and then subtract the y coordinates and square it, and take the square root of all that. So the square root of 5 minus 1 squared, and then plus 4 minus 2 squared would give us the length of PQ. So when I do that, I get the square root of 16 plus 4, which is equal to the square root of 20. And if we simplify that, we get 2 root 5. So that would be this length right here. So this is 2 root 5. Now I'm going to go ahead and do OR right there. So if I do OR, I'm finding the length of OR, the vector. So the square root of the x value subtracted, so this point minus our terminal point, which is at 0, 0. So I have 4 minus 0, 4 minus 0 squared plus 2 minus 0 squared. And when I do that, I get the square root of 16 plus 4 again, which is equal to the square root of 20. And then this reduces into 2 root 5. Now, we've just shown that PQ and OR have the same length, but we're not done because remember vectors have a direction and a magnitude, again length. So now we need to figure out if the direction is the same. So how could we figure out the direction is the same? Well, we can actually just figure out what the slope of each of these lines are. So if you remember your slope formula, you can figure out, let's do PQ first. So we're going to do PQ's slope. So the slope of PQ would be your y coordinates minus your other y coordinates. So let's do 4 minus 2 over 5 minus 1. So we get 2 over 4, which is 1/2. So now if we do OR's slope, we would get 2 minus 0 over 4 minus 0, which gives me 2 over 4, which is equal to 1/2. So again, because the length, and if you notice the slope, is 1/2 for each of these, so the length and the direction is the same, therefore PQ is equal to OR. So you'd have to show both of those. Okay, now we're going to find the component form and magnitude of vector v with initial point at 4, -4, and terminal point at -1, 5. So I already have my arrow here, so 4, -4 would be right here. Oops, a little off. There we go. So this is the initial point here at 4, -4, and then we got the terminal point right here, which is at -1, 5. So if I want to find the component form, that means I need to find what the horizontal distance from here to here is and the vertical distance from here to here. So on a graph, it's easy just to count. I can see that from here to here is a distance of 1, 2, 3, 4, 5, and we are going 5 in the negative direction, so this is 5. And then if you go up 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7, 8, 9. So this distance from here to here is 9. So if we don't have graph paper, then the way that we find our components is just by subtracting them. And remember, the order in which you subtract is important. So you always want to do your terminal point subtracted from your initial point. So the component form for this would be, we use these arrows right here. So we're going to take -1 minus 4, comma, and then you have your y value, so 5 minus -4, and when you reduce this, you get -5, comma, 9. So this would be the component form. So for this, because my direction is going in this direction, we know that we went this way 5, so that's why it's -5, and then we went up 5 to get that to that direction. So that's why our component form would be negative 5, 9. Now I want to find the magnitude. So to find the magnitude of this, I'm just trying to find the length of vector v. So to find the length, I can just use my Pythagorean theorem. So we have the square root of, and we can do one of two things. We can use the points that were given right here, or we found our horizontal and vertical components, and then we can just use that. So that's what I'm going to do. So I'm going to do, in this case, we have negative 5 squared plus 9 squared, which is just the Pythagorean theorem because I'm using this as my right angle right here. And I'm trying to figure out this length right here. So 5 squared is 25 and 9 squared is 81, which gives me the square root of 106. So now I have the component form and the magnitude of vector v. So the next part is vector operations, scalar multiplication and vector addition. Scalar multiplication of k times u is just when you multiply it in. So you can just take that k and multiply it by both your components in your component form. It makes the vector longer or shorter. If k is positive, then it has the same direction. If it is negative, it's going to go in the opposite direction. So we're going to start off with this vector right here, vector v. If we did 1/2 times v, then notice then the length of it would be half, but it's still going the same direction. 2 times v is going to be twice the length of v. And if we did negative v, then it goes in the opposite direction. And if we do negative 3/2 v, same thing, opposite direction, it's going to be a little bit longer. So that's for our scalar multiplication. Now, vector addition, the sum of u plus v is the sum of the vectors. Graphically, the initial point of one vector coincides with the terminal point of another vector, which is called the parallelogram law, which is also said sometimes as the sum of its head to tail, which we'll talk about. When you add two vectors together, this word you'll see when we do the word problems, the resultant is the diagonal of the parallelogram having u and v as the adjacent sides. So when I'm adding these two vectors together that I have here, u and v, the resultant is this red right here. So that's going to be u plus v. And the way that I can find that u plus v is I can just add, we have our head to tails right here with this side u and v and add them together. Or the parallelogram law says that if I move this to here, because I'm not changing the direction of that, nor am I changing the length, and if I move this one here, again, I haven't changed the direction or the length of vector v or u. So if I do this way, notice that vector v here and u, even though I moved it in a different position, the resultant u plus v will still end up being the same. So that's all the parallelogram law states, is that it doesn't matter where the vectors are or how you add them, you'll still get the same answer in the end. So the properties of vectors, addition and scalar multiplication are seen here. You guys can go ahead and read through that. You just really have to be careful when you're subtracting vectors, so always watch out for that. If we look at this first example that I have here, it says we want to let v equal negative 2 5s. Remember, that's the component form, so that means that our horizontal component is negative 2 and our vertical component is 5. And we also have w, which is 3, 4. So if I want to find 2 times v, that means we're doing scalar multiplication. So all I'm going to do is multiply each of those components by 2. So it would be 2 times negative 2, 2 times 5. So pretty easy, and we end up with negative 4, 10. So this would be the new vector, 2v. If I want to do the next one, we have w minus v, and again, it matters in which order you're going to subtract them. So w has to come first, and then v would be the second. So the x's are the first coordinate, so we have 3 minus negative 2, comma, and then we have 4 minus 5. So in this case, you would get 3 minus 2, which is 5, and 4 minus 5 is negative 1. So this would be the resulting vector 5, -1, and again, that order matters in which you subtract it. For C, now we're taking vector v and we're adding it to 2 times vector w. So the first thing I'm going to do is 2 times vector w just to see what that is going to be equal to. So 2 times 3 gives me 6 and 2 times 4 gives me 8. So then I'm going to add this to vector v. So when I add those together, I'm going to have vector v, which is -2 plus 6, comma, and then we have 5 plus 8. And it doesn't matter for the addition which order you do it, subtraction is the only one that matters. So then for this one, I end up with 4, comma, 13 for my component form. So that means I'm going a horizontal distance of 4 and then a vertical distance of 13. Okay, for the next one it says, find a vector equivalent to vector PQ with its initial point at the origin. So if we think about the vectors that we're given, we want to take something that's not at the origin and we're going to put it at the origin. So let's go ahead and get a graph and take a look at this. So for this, since it's vector PQ, that means that P is the initial point, Q is the terminal point. So we have 2 and 7. And then we have Q, which is -2 and 9. So that means that if I draw my vector, be going from here to here. Now, we're trying to move this so that the vector would be at the origin. So when you have a graph, it's easy to visualize this because I can just take this down and then I could see, okay, well, yeah, that makes sense. It's a little too long there. There we go. So now that I have this, if I reposition it down here, then I could see what the horizontal and vertical component is. But let's say I didn't have my graph paper, so then how do I do that? Well, I just want to figure out what the component form is. So to figure out the component form, you're just, remember, subtracting. So for this point, what I would do is that for the component form, PQ would be equal to, remember, component form gives your horizontal and your vertical, so what you need to do is just subtract. It's always your terminal minus your initial. So we have -2 minus 2, comma, 9 minus 7, and -2 minus 2 is -4, comma, 2. So this would be my new vector. And if I bring this down, you can see that it matches up with what we found. My arrow is not exactly perfect. There we go. So now that I have that, I can actually see that I had -4 and then 2. So that would be my my vector that's equivalent to the vector PQ, but its initial point is now at the origin when I'm subtracting it and finding its component form. Because remember, again, the component form is the horizontal component and the vertical component. If I wanted to find the magnitude of this, so the magnitude of PQ, then you just need to use your Pythagorean theorems. So then this is, again, -4, and this was 2, so you're just doing 4 squared plus 2 squared, and then the square root of that. So and then, of course, we can finish. But that wasn't actually what our question was. So let's just go ahead and go to the next one. So for the next one, let's say I don't have my graph paper with me, so I'm just going to do this one by hand. If I want to find the horizontal and vertical component, then I'm, again, just going to subtract it. So PQ component form would be equal to, so this is, again, the terminal point minus the initial point. So your x's subtracted, comma, your y's subtracted. Oops, and that should be a arrow there, not a parenthesis. And then when I do this, I end up with -7 minus -5 gives me -2, comma, -15. And this would then be my vector at the origin. So that means we're going something like this. So we would have -2 this way, and then -15 would be down here. So the vector would look something like that, with the initial points. This will be the -2 and then -15. All right, so what we're going to do is we're going to practice some of this in class.